Okay, welcome back to the next lecture. And believe it or not, we have finished the chapter on vectors. So we will, let's recap some of the summary to summarize everything you need to know. And we'll swiftly move on to the next chapter, which will study some of the applications of this and see how we can now analyze motion and how things move in the world. So traditionally, vector is sometimes a very confusing concept to a lot of people, but now you understand it is actually very simple. It's an arrow, okay? And there's a couple of things, and I think I'll summarize 7 important things you need to know, and that is basically it. Okay, so first of all, the definition is probably the after the first test, you won't need to don't need to recite it anymore. But we'll put it here for completeness, right? So the definition is it's a directed line segment that obeys the triangle rule of addition. The triangle rule of addition. Right? So remember, in mathematics, a line is something that extends out to infinity. It doesn't terminate. A line segment is a segment of that, so it does terminate, right? So it's a finite segment of line, and a directed line segment is a line with a direction, which is just a very, very fancy and convoluted way of saying it's an arrow. Okay, so that's basically the only reason we point out this formal definition is it's telling you there's nothing to be afraid of. It's just an arrow, right? We have a criteria that obeys the triangle rule of addition. We know what that means. It means when you add things, there's this head to tail rule or tip to tail, whatever you like to call it. It kind of forms a triangle when you add it. And that's the basics of everything. And you can sort of build everything from it. Sorry about the glare over there. I'll try not to write anything more there. And it has 2 key properties, right? So every vector possesses a magnitude or the length of it, right? The formal word is the magnitude and the direction. And that uniquely tells you, it defines the vector. And this is often contrast with scalars. So scalars are essentially just another word for number, at least at this level. And for most of your course, you just treat the word scalar just as a number, right? So what is the property? What's the key property of a number? It has value. It has another word of saying that it has magnitude. It has value. And a vector will not only have a magnitude, which was technically the length of it, and it has a direction. And if you can describe direction properly, then you uniquely define this vector. It doesn't matter where it is. Notice that I don't have a property called location, at least at this level. As far as you're concerned, it does not, you don't have to, you can actually move these little arrows all around the coordinates or around the plane if you like, right? But there's a small caveat over here, a small footnote that describing directions properly and defining it completely, it requires a little bit of attention, which you understand, and we'll talk about that. And there's 2 ways to represent it, right? You can represent them geometrically or algebraically. So in the geometric representation, very simple. When you add things, right, you basically connect them, you move them around, right? So even if you have 2 starting at the same point, 2 little arrows starting at the same point, you want to move them so that they connect head to tail. It doesn't matter which one you want to connect, right? Ultimately, you want to sort of connect them that way in order to add. In case it's not clear over there, I'll just copy it here. Algebraically, you realize that you can also write them in components like that. So we usually call that the X component, the Y component. And there's a couple of ways to write it. You can write it in a column, you can write it in a row, or you can write it explicitly in component form like this, right? Using the base vectors, as we'll see, or as you've seen. And this has the benefit of when you're adding things, right? It is extremely easy because you directly just add them straight across using this component algebraic form, okay? So there's 2 ways to represent them. This is very visual, but it's not so convenient in doing math. Even though it makes it clear what's the magnitude and what's the direction, that's very easy to add, subtract, and scale, right? I mean, that's easy, but it's just tedious. You have to take out a grid paper and draw out, take a ruler and draw things out in order to, and then you have to measure the thing. Whereas here you can do everything with algebra. Okay, a couple of notations. Remember what that means. Anytime you have a vector, write it with a little arrow on top, and a vector always consists of multiple components, right? It either have 2 components or 3 components like this, or as a row, you have AX, AY, AZ. We'll stick with two dimension at this point, but every now and then we might see a 3-dimensional one pop in. But most of the time we'll work with 2-dimension. It doesn't make, if you can do 2-dimension, you can do 3. It's not a big deal. But just be careful, never write something like this, okay? I know what you mean. You probably mean the magnitude of that is 5, but this is a scalar and that's a vector, right? What you want to write is this, right? That tells you the magnitude of this guy is 5, right? That is because this is a scalar and the magnitude of something is a scalar, right? But the vector is a vector, it's not a scalar. Here, this is a big no-no, right? You don't want to equate a vector with a scalar. They're not the same. Sorry if it is just in the glare. Let me try to just repeat it over here, right? So don't write something like this, okay? There's sometimes there's the lazy way of writing this. Right? It's just, we'll just write it without the sign. This is given the understanding that I already defined the vector somewhere else, right? If I have a X arrow somewhere, then you can just write X equals to 5. And that's okay because X is the symbol. Without the arrow, it's usually the algebraic symbol, right? The algebraic notation for variables, for scalar variables. So that's good. The length is a scalar, the magnitude is a scalar. That's all good. That's not good, right? And if the vector in a specific case, if it has a unit, if the magnitude is 1, then we want to emphasize that and we use a little hat like this, right? And sorry, we're jumping ahead, but yeah, well, let's complete this, right? A unit vector is basically a vector of unit length, right? Of 1 unit length. Sometimes you hear people just say of unit length. What that means is 1 unit length with in parentheses, right? And we denote these guys with a hat. So if you have something like this, right? Anytime you see some symbol with a hat, that's a unit length. And there's very famous, the famous base vectors. There's a couple of famous unit vectors, I should say, right? It's the ij case. So every now and then we'll talk about the 3 dimensions. And these are unit vectors, so they have unit length, but they lie along the axis. I'll just displace them a little bit so you can actually see them, but it's X, Y, Z like this. Remember, when you draw 3D coordinates, this is the convention. You draw X, Y, Z on the plane and X sort of just diagonally swinging out, representing that's pointing out of the board, right? It's not so easy to draw that, but hopefully that's visualizable. And in 2D, right, just technically I should draw it on the axis, but just want to be able for you to be able to tell it, right? So in 2 dimension, that's it, right? So these are the base vectors, and they're very useful because any other odd vectors, like this guy, right? You can compose them and write them out of how many i's, in this case, how many negative i's, and how many j's you need, right? So that's this component for writing it here or any way like this. And finally, in describing the directions, remember it depends on how many dimensions you're in. In 2 dimensions, how many information do you need to describe a direction completely? 3 pieces, right? You need what angle from where to where. Okay, so what angle from where, or what did I call it? I think I call it which way? Which way from where? Right, so for example, like 30 degrees upwards, or let's say counterclockwise. Let's describe this guy, right? Let's say this is 30 degrees, but you should not just, so what you could do is like say 30 degrees counterclockwise from the positive y-axis. Right, so that's a good example of describing it properly. In 1 dimension, all you need is just plus or minus, because if the vector lies along 1 dimension, as you can see, if it's just around X, you can just simply use 1 piece of information. You can just say plus or minus, and that's good. But always, always, if you're taking notes, remember, put a star around it, you need a system. Okay, a system or a frame of reference. Frame of reference, right? So what that means is you either need a compass if you're using north, east, south, west, or you need a coordinate axis. So you draw the coordinates before you give these three pieces of information, okay? All right, and I think the main thing to take away is know how to manipulate them, know how to add and subtract them, and also another very important thing is to go between these two. So if I'm giving you this, know how to find the magnitude and direction. If you're given the magnitude and direction, know how to find the components, okay? So these are defined by the components in the algebraic representation, and this is defined by the magnitude and direction. So in particular, if I give you the geometric one and ask you to find the algebraic one, that's called resolving vectors. And we'll see that it's going to be very, very useful very shortly. All right, so now we'll move on to chapter 2. And if you haven't already, you can put on Piazza or even in the comments below if you like. Think about what are some of the usefulness of vectors. So this is all very interesting at the moment. We were able to do math and do algebra, right? Do adding arrows. You build the mathematics, build the whole theory of arrows. But what is this useful for, right? You can think about that, and we'll talk about that in the next video.